let me continue with the story. So the goal is to basically show you that conventional Fourier analysis can be derived very simply from just power series expansion, as you know. And the way of generating them can be improved substantially in highly nonlinear ways. Okay, so the tools of holomorphic functions that we use are tools like factorization of functions, various products, composition of functions lead to new versions of sort of wavelet-like orthonormal basis, but they are attached to different dynamics, any dynamic you want, and I'll show you that. And so this relates to all kinds of dynamical systems, which can be obtained by just composing Blaschke functions. So the main, I would say, hero in this story is the Blaschke functions. They're the heroes. So this is really a long-term collaboration starting with Guido Weiss about 1965, really, where I was still a graduate student, and we were factoring holomorphic functions on multiply connected domains. And the magic of the algorithm I'm going to show you was already working over there. Incredible, actually. Then my student Michel Naon, Stefan Steinerberger, Haotiang Wu, Qian Tao, Jacques Perrier, who is a co-author here, and Alec Grossman and Yves Mayer, the origin of sort of wavelet theory and so on. So now, as I said, the main hero here is the Blaschke product, and the point is I'm going to relate Blaschke to a one-layer neural net, and composition of Blaschke product will be several neural net in which the number of layers depend on the number of composed Blaschke product, and you'll see that. You saw a picture at the beginning, which is a phase picture of such a process, and in that phase picture, you'll see every droplet represents a basis function or sometimes a unit in a deep net, and you'll see that. It's sort of amazing that what I'm going to do is really not an invention in any sense. This is all derives itself naturally out of complex function theory. So it's really discovering nature in some ways. Okay, so what is the issue? The issue is that we really don't know how to analyze highly varying oscillatory patterns. So by this, I mean signals in which the frequency itself has all kinds of transients. So the transient is not in the signal, it's only in the phase or the frequency of that. In general, you know, people going down to Gabor and other defined what is called instantaneous frequency of a signal by taking it, projecting it into holomorphic signals and then looking at the phase of that. My point is that that was a good phase, but not good enough. And doing this unwinding decomposition, I'm going to explain in 2 minutes, you do a much better job and miracles occur. So let me start. My assumption is that some of you are not familiar with complex analysis beyond undergraduate. And so I'm going to fill in some gaps. Okay. So one thing, before we do that, let me just say this. Takanaka and Malmquist, 100 years ago, were trying to do the following thing. They were trying to, given a collection of rational functions on the disk or on the half space in the plane, trying to orthogonalize them and build and do Gram-Schmidt on it. And in order to get an orthogonal basis of all rational functions which are in L2 of the disks. Okay. So those are power series essentially, which belongs to H2 space. And they wanted to get an orthogonal basis. Okay, so miracle, this was independent work by the two of them. It's really about 100 years ago, almost exactly now. And it's amazing, but when you take the rational functions with poles at point AJ, 1/AJ, if you wish, which are outside the unit disk, if AJ is inside. And you order them in some ways, and you do Gram-Schmidt. The amazing thing that happened is that once you have the order, first of all, you get a very simple necessary and sufficient condition to get an orthonormal basis of all of H2. Secondly, the miracle is that you can actually explicitly write a formula for this orthogonal basis. So it's completely amazing. I mean, I don't know of any other example where it's so simple to basically do Gram-Schmidt explicitly. So in fact, what's this thing is seeing here is that you look at rational functions with poles at 1 over aj. So aj are inside the unit disk. If the sum of the sum of the distances to the boundary is infinite, you can do the following thing: order the aj in some order, any order you want. Take the product. So define the nth Gram-Schmidt function is the product of those factors. Each one of those factors is a map from the disk to itself, mapping z, if you wish, 0 to minus aj, or mapping aj to 0 if you wish. And it has modulus 1 on the boundary. If you are in the upper half space, you can assume that the poles are down at the bottom in the lower half space, and the rational function you take are z minus aj divided by z minus aj bar. Z has positive imaginary part. So this obviously has modulus 1 on the real line, and here too it has modulus 1 on the real line. Those are conformal map from the disk to itself. Here it's from the half space to itself, maintaining the boundary. The functions are, you take the b and z and you multiply b and z by a Bell function, if you wish, which is 1 minus a n bar z this, and you get an orthonormal basis, which is a miracle. On the half space, it's even nicer because you basically, this is modulus 1, this whole product, and 1 over x minus a n bar is an is in the upper half space, so a n bar is in the lower half space. So this function has a pole in the lower half space, and it's holomorphic in the upper half space. And this is an orthonormal basis. So they discovered it 100 years ago. And some people have used it in a variety of ways. But you will see that it pops out. So this was one thing that was related to Blaschke. So this is a Blaschke product. This is in the upper half space, a Blaschke product from J goes from 0 to n here. So what is the most Blaschke products in harmonic analysis have been major actors for the last century in some ways, in the sense that there's a theorem coming from Blaschke which says that any holomorphic function can be factored as a Blaschke product, an infinite Blaschke product, if it has infinitely many zeros. If it only have a finite number of zeros, it's a finite Blaschke product. So the assumption is the function is holomorphic, and square integrable on the boundary. Could be integrable, so it's in the Hardy space. But this is what it is. So the theorem is that you can factor out all the zeros of the function, and you are left with so the modulus of f is 1, because it's a product of functions of modulus 1. So G that is occurring here has the same modulus as f. And the Blaschke product is a product of the zero. So the alpha k's are the zeros of f counted with a multiplicity. And if 0 is a 0 of order m, this is what the Blaschke product looks like. Okay. Now, it's a very beautiful theorem and was used in a variety of ways to prove theorems in harmonic analysis. Like it allows you to prove that any h1 function is a product of two h2 function, because you could just take f, write it as bg, take square root of g because it doesn't vanish. It is an exponential, so you can compute the square root, and so you have written f as the product of square root of two h2 functions, so that they're all in. So that's how you got h1 factor. So that was the main. There were many results that could be proved with that, and the goal, if you wish, at the time of Zygmunt and various others was to get rid of complex analysis and convert it to real analysis. Anyway, coming to this theorem here, it has one major problem, is that finding the roots of a holomorphic function is a monster pain and pretty unstable and difficult to do. On the other hand, the function g has the same modulus as the function f. So you know, and it is an exponential, right? So all you have to do is just construct g and divide f by g and you get b. This is exactly what Guido and Mary Weiss did in 1962. They had a very short paper of 2 or 3 pages, basically proving the Blaschke factorization for any function in the van Lina class or a Hardy space can be written as b times g. And the proof they have is very simple. They just took the log of the modulus of f, looked at the weak limit of that. It gives you a measure which is log of absolute value of f. If it converges to a function, this will be log of absolute value of f. It gives you g, and once you had g, b was just f divided by g. In general, this has an absolutely continuous part, which is log of absolute value, and a singular part, which gives you a bounded holomorphic function with no zeros, which has only sort of weak limit of the zeros on the boundary. So that was their theorem. That's very nice, but it's a key to success. And I'll show you that this theorem allows you to actually compute everything I'm going to talk about in real time, just running a few Fourier transforms. So let me now, again, go back to Cauchy. As I said, this talk goes back at least 200 years in history. In fact, Fourier is 220 or 230, and Cauchy is the same time, right? So here it is. So take a function, a holomorphic function on the unit disk. At this point, let's assume, you can assume anything you want. It could be even holomorphic on a slightly bigger region than the unit disk. So take f of z and write it as f of 0 plus this function here, which has a 0 at 0. And so you can write f0, fz minus f0 is z times f1. You can pull out the z. And you can iterate this process, take f1, write it as f1 minus f1 of 0, which is equal to z times f2. And you basically get the power series of f, right? So you get that f0 is here, and this will be the first coefficient. Second, you get the power series. And if you let z on the boundary, it's a Fourier series of f, right? So this is it, very nice. Okay, now what we are saying is that we could do the same thing, but instead of write this, look at the first term, but instead of just pulling out 1 zero, let's pull out all the zeros. Okay, so if I'm pulling out all the zeros, I'm writing this as f1 plus b1, which is a product of all the zeros, a Blaschke product of all the zeros of f, and g1. And then I can take g1 and write it as g1 minus g1 0, and I get this one itself is factored. And so I get a series which is f of 0 plus a number, which is a geometric mean of f, exponential, yeah, the geometric mean of f. And then I have an x number, and then b1, b2. So you see, b1 oscillates. I mean, the point is b1 winds around the circle as many times as there are zeros, right? The winding number of f, the winding number of this thing tells you the number of zeros that you have. And so this could be, if it has 50 zeros, it'll be essentially 50 oscillations. This one will be the first group of oscillation times the second group of oscillation. And first group, second group, third group, and so on. So this factorization, this gives you essentially the analog of a power series where the coefficients are the non-oscillatory part of each one of the preceding terms, and then a function here that occurs here. Now, I should have said that, and we'll get to it. The oscillation of B1, B2, etc., is always in the positive counterclockwise. So the phase of B1 is monotone increasing, the phase of B2 is monotone increasing. In the case of a Fourier series, the phase of B1 is a constant, n, but all the integers you get with positive integers. Here, the positive integers are replaced by the fact that the phase of this product is a sum of two phases which are monotone increasing. So the derivative of those phases are positive, right? And so it means I have positive instantaneous frequencies. So this is what one gets. So already this term by itself, by the way, we'll see example, is quite magical. Okay, it's an oscillation around the circle at variable speed. Okay, but always in the positive direction. You're not going forward and backward and forward and backward. It's positive. And G1 is sort of like an amplitude term, right? So you look at this, it has a oscillatory term and a complex amplitude term. We will see a lot of examples in a minute. So the problem with this algorithm, while I'm sure that somebody may have thought about it years ago, that it's totally impractical the way it is because you can't find the zeros. On the other hand, if you just do what I just described a minute ago, which is a Weiss algorithm, observe that the modulus of f and the modulus of g are the same. So log g is known, and log g is it doesn't vanish in the disk, so it's a holomorphic function in the disk. So the projection of log, so I know the real part of log g is equal to log f. So log g is a projection of log f on holomorphic functions. So g is e to the projection of this function log f onto holomorphic function. And b is just f divided by t. So I just need to compute that. I just need an FFT, a single FFT. Just expand log f in a Fourier series and just keep only the positive Fourier frequencies, right? And that's it. And if I don't want to factor all the zeros, I can just project log f on the first 100 positive frequencies, and I'm finished. So I just did one factor with frequency at least 100 with one short FFT. Okay, so it's relatively easy. By the way, look, I may be going too fast. I may be going too slow. So please, and if you have any questions, just interrupt me. Don't worry about the fact that you are muted. Unmute yourself and just do that. Or raise your hand and whoever is watching it will unmute you. So in any case, this factorization goes like this. So this is what we call the unwinding factorization. We take the function gn, it has a constant value at 0, then it has the gn minus gn0 has to vanish, so it has to wind around the circle at least once, but it may have all kinds of other zeros. So each one of them accounts for one time that this difference winds around the circle, right? And so you get this, so you got gn plus 1, and this is just the whole algorithm is just that, right? And so you get an expansion. Again, I'm repeating the same expansion for a good reason, which is the first term is just this geometric mean of the f, and then I have the zeros at zeros. Then the next one, I have the zeros of the next term times the zero of the first term, and so on. So I get a sequence of oscillation around 0, which is increasing, which is clearly larger than the number of terms that I have, which tells you that this sum, if I stop here, and I expand it in a Fourier series, the Fourier series will start at least at n to the k, which implies that it will have to converge, right? And it will have to converge faster than the Fourier series of the corresponding regular Fourier series. I'm basically peeling off highly oscillatory terms of this thing. So this converges, in fact, much faster than the Fourier series. And each one of those terms is a very pure phase term. It's e to the I, phi 1 plus phi 2 plus phi 3 plus up to phi k, where each one of the phi is a monotone increasing function in this. So it converges quite nicely. It's very easy to prove that you have convergence in LP for every p larger than 1. and it converges, so in HP and so on. In fact, this thing relates to some things that some of you have seen, which is the theory of invariant subspaces of HP, and I'll get to that in a minute. But let's look at some examples here. So here's an example. By the way, most of the numerical and implementation and playing the pictures here and so on come from my student Michel Naon about almost 20 years ago, I would say. And here we just wanted to see, here's a signal, which is basically two pure frequencies. The real and imaginary part of the analytic signal are given here. As a complex signal, it winds around this way. There are two amplitudes, and like that. And when you decompose it, the G, decompose that signal, the G looks like that. It never vanishes really. And this winds around. And the B, which has modulus 1, is just like that. So the frequency is very nice, and this is okay. But here is first miracle that was occurring. Suppose now your thing is noisy. Well, it turns out that most of the noise is peeled into the G. It's a multiplicative noise in some sense. It's peeled, goes into the G, and the B, which is purely oscillatory, is a very nice winding function, and we used it in a variety of applications. You'll see in a second. Here's another example used for essentially looking at blood pressure or it's a respiratory signal in which you have the pressure of in the lungs and the oscillation. So there's a basic, the signal is a blue one up here. There's a basic oscillation going out, and then there is a variability from that. So the first term in this decomposition reveals the first carrier, if you wish. And the second term is this one. When you add up this first one and the second one, you have basically essentially completely rebuild the signal. Okay, so the signal that's rebuilt is not identical to what you have here, but it gets pretty close. At the time, Michel Naon even proved, and we have done a lot of experiments, that the series converges exponentially fast to signals which are quite noisy. I mean, basically, you can take a random Fourier series and try to see what happens to a random Fourier series. The various terms you get captures a series. Within 4 or 5 terms, you capture the series incredibly fast. So this is, in a way, the complexity goes into the location of the zeros and how they go. And I'll refer to that. By the way, I will try to indicate that what has happened here is that this decomposition is sort of a decomposition into some sort of natural musical score. The Blaschke factors are really like musical notes in a way, and we'll see that in a minute. But first, let's look at that. If I look at the F minus its projection, minus the first term, I get this function has, I've basically taken F, it belongs to, this belongs to the space B1 times H2, and the terms of the projection, so B1 H2 is a space of function vanishing at the same zero, having zeros which are the zeros of B1. That's an invariant space where you multiply by Z, it stays invariant. And the famous theorem of, I think Helson-Laudenslager, I think so, was that all spaces of subspaces of H2, which are invariant, are of the form an inner function times H2. So inner function is a function which has all the zeros inside times a singular function which has sort of weak zeros on the boundary in some ways. But the decomposition is sort of a projection pursuit times type decomposition. One other thing you can see very easily if you just try to represent what I have. So now we see some nice colored images. So this is the phase of the analytic part of this function that occurs here. This is sort of a In fact, it's written, the function is described here. It's a polynomial with zeros at the endpoints here. So each one of those endpoints correspond to a zero of the function. And when you look at the phase, you immediately found the zero. So I can take the modulus of this function, divide by the log by the function g, and I'll get a function whose phase is described here. And I've discovered now I have an algorithm to find where the zeros are approximately. By the way, usually it's pretty unstable numerically, but this method works incredibly well. And I've essentially completely analyzed. There's a function having 1, 0, some oscillation around here, some oscillation at that scale, some oscillation at this scale. And we'll get back to many more fascinating examples. So here again, this is an example of two signals at different frequency. Combining, they look like this. When you do the Blaschke, you get it back in a second. So Haotiang. But one application, which was fantastic, that Dennis Healy obtained, as you see in 2009, this is immediately after Michel Naon was doing that. Dennis was very excited by this thing and decided that this might be a very good way of understanding, of computing Doppler shifts. So the situation here is this: you send a fixed frequency signal, acoustic signal, say on something that is moving or variable. In this case, it's a blood flow. You basically have a, you want to know what the velocity of blood is in the arteries. You shine in a fixed frequency acoustic sound, and you get a return in which the frequencies are shifted. And Doppler will tell the velocity of the blood will tell you how it should be shifted. So you see on this picture that the big thing here is what the best Doppler can do for you. The frequencies, the basic frequencies that the one term of Blaschke does is the one that's down here in the middle, which is basically within the bar lines that you expect. So it's extremely useful. The reason Doppler does not work too well is that the velocity of the sound here and the velocity of the blood are sort of too close to each other to see, to basically measure it well. And Blaschke does a pretty decent job in that. Another example of this kind is if you look, the gravity wave measurements that were done a few years back, basically measured two oscillatory chirps, which come in from the model of essentially the black hole thing, and which basically has to generate a gravity wave whose pitch is changing with time. So when you look at the gravity wave at one location and then at another location, you get two chirps, which are not exactly the same. You want to model them. You get in immediately with a pretty decent fit between the two locations, and the pitch, the instantaneous frequency in one and the one in the other sort of fit together very, very nicely. People who were doing that were using sort of local Fourier analysis of the kind that, well, it's another story, it's another way of doing things. So let me continue with the story. So this is how it was 2 or 3 years ago, but let me show you how one can analyze. I mean, the point of this is that you can analyze signal whose frequency exceeds anything you want, right? So in particular, take the signal on the circle, which is e to the I, or e to the minus 2 over 1 minus z. So when z is 1, the imaginary part blows up. You can also take this thing here, which is e to the I 1 plus cosine theta over sine theta. When theta is 0, this oscillates infinitely often. And so it's a signal it's a bounded holomorphic function. which oscillates incredibly on the boundary at zero. It has infinitely many oscillations at zero. On the other hand, the zeros of these functions are roughly at the point, the frequencies, you can easily compute the derivative of that. It looks like 1 over theta squared. This is like 1 over theta. So the derivative is like 1 over theta squared. So the frequencies are 1 over theta squared as theta approaches zero. So the closer you are to the point 1 in the unit disk, the faster the thing oscillates. And you see that when you compute exactly the zeros of that, which I will get to in a few minutes, they look like each zero corresponds to one frequency roughly of the order of the derivative of that at k squared. And now we want to see, so what is the analysis of this thing? How does it really look? So if I plot the phase of this Blaschke product of that, so here, this is the phase plotted. It really should be, this line, which is a straight line, is artificial because I wanted to discriminate. It's really, this axis y here, the distance to the boundary, was replaced by its square root. So this is why I get a straight line here. This should be viewed as, the distance here should be viewed as 1 over x squared, right? And here it looks like basically just x really. So this is a phase. So you have to invert, to get the frequency, you have to invert this distance. Okay, so here each one of those locations correspond to 1 zero of this function with higher and higher frequency as you approach this particular point. Each one of those droplets is one of those, each one of the end of those droplets here is one of the zeros. So you have to, you can read this. I mean, if I plot the phase of this single Blaschke product, you can read this as the Fourier analysis of this signal, which is, if you wish, 1 over x squared, which is 1 over x really. It's e to the I over x. Coming back here, it's e to the I over sine theta. 1 plus cosine doesn't matter. This is just so that I can compute exactly what is going on here. This is looking at the function e to the I 1 over sine theta. By the way, the functions you can analyze with this method could have singularities in the frequency domain at every rational point on the circle. And you can still analyze it. So they're sort of beyond, what I'm trying to say is that we are here already beyond Fourier analysis, in the sense that we can analyze functions which are completely, incredibly highly oscillatory. In fact, you can have fractal oscillations in the system here, and I'll get to that. So what you have here is that each one of those points is the presence of one frequency contribution to the boundary function that is like 1 over, if you think of this, instead of theta, think of it as x, the function would be e to the I over x. And as I approach zero, I have more and more notes participating in the music of e to the I over x, right? So cosine, sine of 1 over x is sort of the oscillations that you have here, or cosine of 1 over x. So it's quite remarkable that you can do this kind of analysis, and in fact, it's really not particularly difficult, but it's highly nonlinear. So I'm going to switch for a moment and see come back to the Takanaka type basis I had before and ask myself, can I use that? And can I use, and I have to use infinite Blaschke product in this case, to build a basis of the upper half space, which is shift invariant and scale invariant. So I want to build a basis of Hardy function, which is like a wavelet basis. So as you know, wavelet bases are characterized by the fact that they look like this. There is a single wavelet phi, so that all the basis functions are of the form phi 2 to the n x plus j, where j is an integer and 2 to the n is a frequency, and the standard wavelet basis as done by anybody doing wavelets, whether it's Mayer wavelets or Doppler wavelets or Stromberg wavelets or anyone you want, they're all of this kind. And it was well known for a long time that on the Hardy space, you cannot really do that. But you can almost do it in the sense that there exists a function phi like this, and then there is a scaling function that needs to be added. So this just depends on scale, doesn't depend on the shift. So that this function here, this collection will give you an orthogonal basis of Hardy space. By the way, the function phi is very simple. It's just a gamma function at x minus 1 plus I over gamma of x minus y. So that's a beautiful miracle. And so let me just explain this in a minute. So what you do is just in the upper half plane, pick zeros, which are the grid point of the hyperbolic grid. So in other words, the point 2 to the n j. So at level 2 to the n, you shift by 2 to the n. At height 2 to the n I, you shift by j times 2 to the n. So on level 1, you take all integers at height I. At level 2, you take all integers at height 2i. Level 3, all integer at height 4i, etc. Okay, so level 0 is height I. So you do that, and you can build an orthogonal basis a la Takanaka Malmquist. All you have to do is order those points, which are in the upper half plane, in some total order. Okay, so you do a lexicographic order. In some sense, you can order the points on the horizontal line and then take the full product on the horizontal line and multiply it by all the products on the line above it. Now you've taken the Blaschke product of all points above a certain point, and that will going to be your order. So this is what you do, and this is how you get your orthogonal basis. By the way, this is a construction I think Stromberg and I tried to do several years ago, but we never finished the calculation. But it's really very easy. So in other words, take the Blaschke product, j going from minus infinity to n of x minus j minus I over x minus j plus I, which is a Blaschke factor, put a Blaschke convergence factor, and take this, it's just equal to a product of two gammas. Take the product from minus infinity to infinity on the whole line, you get the usual formula for gamma gives you that this is sine of pi I minus x or pi I plus x, just the identity on the gamma function. So you get that the product of all functions on the given horizontal line is just a ratio of two sines. And then the one preceding that is a product of all such functions on different scales, followed by a short product going from minus infinity to n. And so you end up altogether that this function here, so gamma x minus 1 plus I over gamma x minus I times this function delta at level n is an orthogonal basis of the whole thing. Okay, so this is great. I did something nice. I'll show you a different way of doing it, which is actually more interesting. So this is the kind of the phase of the holomorphic wavelet looks like that. So you see in other words, they are located at those locations. So I'm going to move now to dynamical systems. So this is great. I have exactly the right amount of time. So consider, a Blaschke function, 1 minus az over 1 minus a bar z, as a function on the circle, right? It just maps the circle into itself with speed which is variable. In other words, the derivative of the phase of that is just the Poisson integral, the Poisson kernel at the point A, essentially. So this factor here is one oscillation around the circle. This factor here is another oscillation around the circle. So this function beta 1z oscillates twice around the circle. If I compose beta 1 with itself, it will oscillate 4 times. If I compose it again, it'll double the number of oscillations. So every time I compose this function, so if I take a function beta n defined recursively this way with beta 1, I'll get a function which has twice as many oscillations as a preceding function. So this is a very simple dynamical system, right? So it's like having, it's like the usual thing that people do, you know, with take z squared plus a constant, iterate it a certain number of times, and ask yourself what happens as you iterations go to infinity. Well, this is the same thing. This is like a z squared, right? If a is 0, I'm sorry, if, yeah, you can take z squared here. So this will be iteration of z squared will double the frequency every time. So this is a dynamic doubling of frequency. So beta nz is a Blaschke product, right? The composition of two Blaschke product is a Blaschke product. That's quite obvious, right? Because you just, the composition of two functions like this is another function like that. Right? It's quite clear. So beta n is a Blaschke product with 2 to the n zeros. So I double the number of zeros every time. And I can take, so since I have a Blaschke product, I can take all the subproducts to generate a collection of functions orthogonal to each other. So the subproducts of a Blaschke product give me automatically a collection, because then I have, provided I order them appropriately, a collection of functions which is a Malmquist-Takanaka basis. It really should be Takanaka-Malmquist. I think Takanaka preceded Malmquist by 2 years. So the composition of two such things is another Blaschke product, and we get automatically, so starting with this, by looking at the iterates, I automatically generate a basis of Blaschke functions, which essentially is multiscale, because each iteration doubles the scale of the number of zeros, right? So I can do exactly what I have here. Okay, I will not go into that if you want to look at the PowerPoints, but basically you can do what one does with Wavelet. You think that the Blaschke function beta n here defines a space of functions which are basically orthogonal to beta n h2 is a space of function which has all the zeros. A space orthogonal to that is a space which I will call Vn, which is a function at scale n. The orthogonal projection is given very simply by essentially the usual projection. So all LP things are correct. I can define a space Wn of a basis obtained by computing the roots, the new roots that beta n plus 1 provides over beta n, and you get that. Again, it doesn't matter. Let me show you the pictures. So here you take this function z minus a over 1 minus a bar z times z. A is a half plus 0.1 I, if you wish. So this is in the upper half. Well, this is mapped. Yeah, this is in the disk. The picture I have here is that I mapped the theta into, I write the points on the disk as e to the minus x plus iy, where x will be the theta thing. No, e to the minus, I have it wrong. E to the, yeah, this is the coordinates I'm taking here. So the phase of the Blaschke product, okay, so each one of the zeros here, so this corresponds, this is a disk sort of straightened out by replacing r by e to the minus x, okay? Or in this case, x is a vertical axis here. So r is replaced by e to the minus x. So this corresponds to 0 in this case, and then you have the zeros of the first function, there are 2 zeros, the zeros of the next layers, there are 4 of them, and every time I double the number of zeros, I get essentially a wavelet basis. So the wavelet basis is a collection of all Blaschke functions which are ending up at the tip of the droplets occurring here. If I start with a function of degree 3, then every time I iterate, I triple the number of zeros. Okay, so I start here, and I get three kids, and I get a triadic tree, and I can continue like that. Okay, so this is fine. So how you generate things is interesting. By the way, there's no reason to iterate the same function. You can take a function and just compose it. You can have a string of irrational functions and just compose them one with the other. I will relate this to a neural net in 2 minutes. Here's another example. This is a function that I described before, which is a product at level 1. Look at zeros, which are of the upper half space. Look at all the points which are at integer, all the integer points in the upper half space. When I take this Blaschke product, I get this function here. That's a function I used before to have Blaschke, the wavelet basis on the upper half space by taking the hyperbolic grid. So this function has, again, infinitely many zeros. This time, the zeros approach quadratically the region. I did not do the stretching that I had before. So this is how it looks exactly. You see the frequencies go parabolically as I approach zero. The instantaneous frequency is 1/x², essentially, as I approach zero. And that's a complete Fourier analysis of this function, which is quite remarkable. But now what happens if I take this function and iterate it, compose it with itself? Just for fun, right? And so let me do it here, and then I'll come back and explain what it means. So this composition of this function of itself sees, you see the level, sort of the mother function, sort of staying there in the background, and then it splits into other spiders. So this looks like a spider, and the spider has kids which are other spiders and other spiders, and so this blows up. This is just 2 layers, okay? I just compose the function with itself, and I get this large, basically, essentially, well, it had infinitely many roots to begin with. So this is infinitely many units here. I will call each droplet a unit for a reason that will become clear in a minute, and I'm getting back here. So let me explain how this relates to what is usually understood as a neural net. So look at the function b, which is a Blaschke product, on the upper half plane. Okay, so it's z minus ak divided by z minus ak bar. The phase of this b is e to the I phi x, where phi, with the derivative of phi, is just, so bear in mind, a is alpha k plus I beta k. So alpha k is the location of the zeros on the line, beta k is the imaginary height of the zeros. The derivative of that, of this phase function is exactly equal to that. So this proves 2 things. First of all, this phase is monotone increasing. This is a positive function. It's a Poisson kernel. The integral of this phase is 1, right? This integral of that is 1. The primitive of that, which is a phase, is just equal to the arctangent of x plus pi over 2. At minus infinity, it's equal to 0. So it's a sum of what are called sigmoids. So this function looks like that, right? So this phase is what is called a 1-layer neural net, where the units of the net are shifted. This is called the bias, and their frequency, if you wish, or the amplitude in the term is given by the beta k that is occurring here. So this is a 1-layer. So the weight is beta k. The shift is alpha k over beta k, or just alpha k. And this is just a 1-layer neural net. I don't know why it's annotating for me. I didn't want to. It's okay. So that is what is happening here. And by the way, a deep net is a composition of such objects. So a neural net, usually the basic function is going to be a sigmoid like this. And that would be maybe the characteristic function or the Heaviside function, or could be the function which is the signum, this could be not the signum, the positive part of that, which is called the ReLU net. So the derivative in that, this would correspond to this, to the function phi here, which is monotone. A ReLU net will be of that kind. A deep net is just you take such a function and you compose it with itself. Here we do something deeper. We are taking this function, composing it with itself as a function on the circle, but it's really composing the phase as a monotone function on the covering of the circle, on the line, right? And this composition gives us the dynamical system that I had before. And it shows that when you do this composition, although you started with relatively simple function, and before I started with a single Blaschke function of degree 2, when I iterate, say 10 times, I get 1024 units, which are the orthogonal basis function of the circle. Okay, so it proves very simply, just because of the dynamics of the system, that you can generate any sort of basis function corresponding to any sort of rational dynamics you want on the circle, which could be relatively, people doing dynamics know that you can generate dynamics with unbelievably complicated fractal behavior. And this is exactly what is happening. So here I went this. So this is just 2 layers. When you go back to my first picture on the cover of this talk, it's just some compositions, but we have done experiments with Jacques Perrier and I were playing with it. And it's directly related, you can relate it to any sort of fractal measures on the boundaries, any kind of dynamics on the boundary you want. The fact that we put in a neural net is just curiosity in a way, but on the other end, you know, complex analysis is a deep field. And we really understand how rich it is in terms of building all kinds of complicated holomorphic functions, you know, from the Riemann mapping to whatever other dynamical system you generate, from Mandelbrot sets or other dynamics, right? The point I'm saying is that this dynamic is connected to Fourier analysis. If you view the functions that you generate and their zeros as building blocks of the kind of oscillation, the kind of windings that you do. And so I think, yeah, I had a few more slides, which I'm not going to deal with, just to tell you that this occurs in nature all the time. This is, for example, a slide of acoustic potentials, e to the ik x minus y, of a curve in the plane like that, which means that you want to know if I have some signal out there, what am I going to measure at various places? And you immediately see that when you just look at the kernel, that if you have a signal f of y, what you get out there on the circle as an output is going to be exactly the kind of oscillatory signal with incredible variability depending on the complexity of the geometry that you have here. And you can go, well, there are all kinds of examples like this. I'm going to stop, but let me just discuss some of those papers here for a second. So Grossman and Morlet and Cournot-Martinet use that to do pattern recognition for audio, essentially recognize in music all kinds of subtle patterns and very precise transitions in frequencies that occur. Then Grossman and Morlet, where they sort of discovered independently Calderon's formula for wavelet analysis, and we're very happy about it. So they started to look at Hardy functions. This is why I'm referring to them, and that's it. Other people build things of that sort, like Eisner and Perp. Weiss and Weiss I referred to before. Let me just say that Guido and I, 2 years later in 1964, really, use the same observation that they had to do sort of factorization on multiply connected domain. And we discovered incredible miracles of a different species. So we found out that Blaschke factors were products of conformal maps from domain onto disk with slits and so on. Then Tao-Qian has done quite a bit of work using this as a tool of analysis. And Michel now was it first introduced this wavelet, basically unwinding decomposition. He was my PhD student. Steinerberger and myself proved some things, and Jack and I did that. I think if you're interested, it's a lot of fun. I think the pictures are amazing. If you have any questions, this is it. This is the total, all I had to say at this point.
Rafi, thank you so much for a great talk. We really appreciate it.